We've seen how to calculate built-in potential, and now we would like to calculate the depletion width. You will see that depletion width is going to play a critical role in the operation of semiconductor devices. So what is it? So to calculate that, let's just refresh these definitions. So xn is going to be minus xp. This is going to be 0. So I'll call the entire region between xp and xn, minus xp and xn, as width. Okay. And we have already seen that xp times na is going to be xn times nd. And the way we have defined it, xp plus xn is going to be your depletion width. All right. So now we would like to get an estimate for w, or calculate the expression for w. Okay. So I'll rewrite this expression. I'll simply say xp times na is going to be w minus xp times nd. Right. So I'll take it to the other side, and then I'll take the na other side. So this is going to be xp is going to be nd by na plus nd times w. All right. So this is how your depletion width in the p side region is going to be, and analogously you can verify that xn is going to be na by na plus nd times the depletion width. Okay. So let's consider a case, right? So whenever you see expression, right, it's always useful to put in some numbers or just take the extreme cases and analyze. If you do that, you will see that you get a lot of more insight. Okay. So let's assume what happens. Let's consider ND is much greater than NA. What would you expect? What does the formula tell us if ND is much greater than NA? If ND is much greater, then XP, well, ND is NA is not going to be significant. So this is going to be almost equal to ND. So XP is going to become W, almost equal to W, right? So essentially what this is telling us is, if one of the doping concentrations is higher compared to the other, the depletion region will be entirely in the lower concentration region. In this case, Na is lower, right? Na is lower. So the depletion region is going to be entirely in the p-type region. Similarly, if you had a situation, if Na is much greater than Nd, then you will see that Na is going to be, when this is going to be on Na, so Xn is going to be, implies Xn is going to be W. So if your p-type region concentration is high, then depletion region will lie entirely in the n-type semiconductor, almost entirely. Okay. So this is the inverse relationship that you will see time and again. Okay. All right. Let me see what is the electric field. Right. We derived expression for electric field. The peak electric field, I'll call it as E naught. E naught is going to be what? So remember, dE by dx is going to be Q Na by epsilon silicon. So Q Na divided by epsilon silicon, and then there is a term which is containing X. In the n-type semiconductor, of course, there's a minus here. In the n-type semiconductor, it has to go to 0, right? So it was basically Xn minus X. It was. Now anyway, X equal to 0, so it's going to be Xn. Okay. So you might have some difficulty in following. I'm just. It might seem that I remember these expressions, but actually in my mind I'm trying to derive it as I'm talking. So you should also be comfortable doing that. Okay. So this is Xn, and we know what is Xn, right? Is it correct? I wanted to write it in the p-type region. In the p-type region, because I put Na, right? So it should be Xp. Okay. In the n-type region, it's going to be Xn. Remember, always the total is going to be Xn, Xp times Na is going to be Xn times Nd. Okay. So since I wrote Na, I'll write it as Xp. And so this is going to be minus Q Na by epsilon silicon times I'll substitute this expression for ND, sorry, P. I'll say that this is ND by NA plus ND times the width. Okay, so this is going to be turning out to minus Q epsilon silicon NA by Na plus Nd times the width of the depletion region. Okay. And once we know the electric field, we said we could also derive the built-in potential, right? Remember what was built-in potential? So if you have a X this way, and let's say this is E you're plotting, so this is going to be your electric field, correct? So this is your E of X. And we know what this quantity is now. This is E naught, right? And this is equal to E at X equal to 0, right? And we know by definition, this is your width. So the area under the electric field was the built-in potential. So now what is VBI, built-in potential, is going to be simply half base into height, area of the triangle. So that is going to be half. What is W anyway we want to find out. So electric field was, I'll take the positive number, I don't need the negative thing. So epsilon silicon NA by Na plus Nd times width square. Okay. So the width of the depletion region is going to be square root of 2 epsilon silicon by Q Na plus Nd divided by Na Nd times the built-in potential. Okay. So I will urge you to sort of get comfortable with the derivation, because we will discuss how the width of the depletion region is going to change with voltage in the next week. Okay. So this is, so far we have not applied any voltage, but this expression is going to change when you apply voltage. Okay. We will use that to analyze PN junctions. Okay. So this is your depletion width. And I could actually calculate these things. Okay. So I've taken another example from 7.2. There is a solution in the textbook. You can verify if you have any doubts. So essentially, you're given basically a semiconductor with Nd, Na, and asked to calculate the space charge width, which is essentially W, in the electric field. So what is I'll just rewrite these expressions. My width of the depletion region just now we saw was square root of 2 epsilon silicon divided by Q Na plus Nd, I believe, divided by Na Nd times VBI. Okay. So if you want to calculate the width of the depletion region, we need W. Sorry, VBI. What is VBI? VBI is going to be KT by Q ln of Na Nd by Ni square. So, well, yeah, this is the number we calculated already. This was 60 millivolts into 31 into 11. So that was going to be 0.66 volts. Well, I mean, you can calculate the exact number. I don't know. I mean, it will be some 6364 something. Okay. Yeah, approximate. This is approx. Okay. So in the lectures, I'll always just leave it as approximate numbers. You please make sure that you calculate the right numbers in the assignments and the test. Okay. So so now we got built-in voltage, so we can easily compute. So I mean, I could leave it to you, but I just want you to note one small thing here, or a couple of small things. So 2 into epsilon silicon. What is epsilon silicon? Epsilon silicon is going to be permittivity of silicon. Epsilon relative permittivity of silicon was 11.7. Okay, I didn't tell you, but relative permittivity of silicon is 11.7. And epsilon naught in semiconductor physics, the tradition is to use uh, 10 power 14 farad per centimeter. Remember, we are using carrier concentrations in per centimeter. So even epsilon naught, we should use it in per centimeter. And that's why in semiconductor physics, most of the time you see that they use this expression into 10 power 14. In regular physics, you'll see 10 power 12 per centimeter, so it becomes 10 power 14. So that's one thing you need to, whenever you're calculating these weights and electric fields, you make sure that you put in the right epsilon. So 11.7 into 8.85 into 10 power 14 divided by the rest of it is same anyway. Okay, so this is going to be 10 power 15 plus 10 power 16 divided by 10 power 31 times 0.66. Okay, I'm not going to calculate this, but I just saw before the class, I think this turns out to be about 9.95 micrometers. Okay, and this is essentially typical number for depletion widths. Okay, so this was 10 power 16 and 15. You'll see that, you compute for multiple concentrations, you'll see that it's a typical range. Okay, typical W in the range of 1 to 10 micrometers. Okay, and it's also quite large actually. Okay. If you go to high dopings, the depletion widths will reduce. Okay, all right. And just one final point before I stop. This is the total width of the depletion region, right? So this was xn plus xp. How much is xn? So if you want to calculate xn, you have to take the opposite concentration, which is Na divided by Na plus Nd times the width. Sorry, the depletion width, yeah. So Na is going to be here 10 power 16, right? So 10 power 16 divided by, well, I mean, 1.1 into 10 power 16 into 0.85, no, 0.95, sorry. Okay, so this will turn out to be whatever, I don't know, it's going to be almost equal, I mean, less, right? 1 by 11, so 0.95 divided by 11, I don't know what it is. 11, no, 1.1 actually, not 11, 1.1. Yeah, 0.95 divided by 0.1, 1.1. So this is going to be something in the range of 8 0.85 microns or so. Okay, approx. Okay, whereas what is XP? XP is going to be in the p-type region, you want the depletion width. So you have to take the n-type concentration. So Nd divided by Na plus Nd times the width. So this is 10 power 15 divided by 1.1 into 10 power 16. So now it's going to be 0.95. So that's going to be 0.95 divided by 11. So this is going to be 0.085 or something. Okay. So this is how the calculations can be done. Okay. So please make sure that you take these numbers and then verify it. And okay, yeah, well, I didn't calculate what is E naught. E naught is simply going to be E naught, electric field peak, is going to be, you can take Na divided by epsilon silicon into XP. And you will see that this is going to be in the range of, some 1 into 10 power 4 volts per centimeter. Okay, 10 power 4 volt per centimeter is actually substantial amount of electric field. Okay, it's not a small electric field. So because it's only confined to this 1 micron region, right? Almost 1 micron region. Even 1 volt is going to give you a large field in the depletion region. Okay. So with that, I think I hope you got a glimpse of how to analyze PN junctions, the basic electrostatics, and how to calculate these quantities, the width of the depletion region, the peak electric field, the built-in potential for various scenarios. All right. So please take some time to review this. In the next lecture, I would still continue with electrostatics of PN junction, and I'll take some special type of junctions. Okay. I'll deal with P plus N junction or one-sided junctions. I'll just briefly explain what they are, and then I'll talk about PIN junctions, and then I'll take a couple of interesting problems. Okay, so that will clarify your concepts. Okay, and then finally, I'll also take a short demo in the next lecture, wherein I'll use a tool on NanoHub to show you how the exact calculations compare with the depletion approximation that we've used in the class. Okay. I'll also use this, as a homework. I'll post some problems you have to calculate manually and also compare with the exact answers. Okay. So yeah, with that, I would like to stop. Thank you very much for your attention, and I look forward to seeing you in the next lecture.